On August 7, 1942, a substantial force of 16,000 United States Marines found themselves navigating the challenging, chest-deep waters as they disembarked onto an unfamiliar landmass, a place many struggle to properly articulate: Guadalcanal. This particular location, a sweltering expanse of dense jungle nestled within the Solomon Islands archipelago, presented these servicemen with a seemingly straightforward directive: to seize control of an airfield currently under construction by Japanese forces. With remarkable efficiency and unexpectedly minimal opposition, they secured their objective within approximately 36 hours. The Japanese contingent subsequently withdrew into the surrounding jungle, leading to an initial impression that the mission had been successfully concluded. However, this early assessment proved to be profoundly mistaken, as the true ordeal was only just commencing. The subsequent events would reveal that their perceived victory was merely the prelude to an extended and harrowing struggle. The captured airfield, far from being a fully operational facility, was little more than a rudimentary clearing in the dense tropical vegetation, its surface a testament to the harsh environmental conditions. This was no ordinary earth. It was an unforgiving tropical soil, subjected alternately to the intense, dehydrating glare of the equatorial sun and the relentless, pulverizing force of monsoon rains. In its dry state, the ground attained a formidable hardness, akin to concrete, yet with the onset of precipitation, it rapidly transformed into a treacherous, viscous substance reminiscent of thick chocolate pudding. Confronted with this challenging terrain, the Marines quickly grasped that this seemingly innocuous strip of land represented an existential threat, capable of imperiling their entire operation. A critical, often unspoken truth of island warfare in the Pacific theater began to emerge. Victory was not achieved merely by occupying territory, but by decisively asserting aerial dominance over it. Without a functional runway, the essential prerequisite for controlling the skies remained unattainable. We urge you to stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The Japanese command, fully cognizant of the strategic asset they had forfeited, wasted no time in retaliating. Within a matter of days, their bomber formations commenced a relentless assault on Henderson Field, a name bestowed upon the airstrip by the Marines in honor of a pilot who had fallen at the Battle of Midway. Yet, the most formidable adversary was not the explosive ordnance raining down from above, but the insidious and pervasive mud beneath their feet. Following each torrential downpour, the runway became utterly impassable. The precious Wildcats and dauntless dive bombers, constituting the sole aerial protection available to the beleaguered Marines, began to succumb to the mire, their landing gears sinking perilously into the saturated ground. Mechanics watched with grim fascination as entire landing gear struts vanished into the thick, clinging muck. In one particularly dramatic incident, a pilot attempting to launch an intercept mission found his aircraft's wheels carving trenches 4 feet deep before the plane could even begin to accelerate forward. He failed to achieve liftoff, and the Japanese bombers he was meant to intercept arrived unmolested a mere 20 minutes later, underscoring the dire consequences of the incapacitated runway. Engineers on the ground tirelessly experimented with every known method to stabilize the runway. They initially attempted to reinforce the surface with crushed coral gathered from the nearby beaches, only to witness it being completely washed away during the subsequent deluge. Next, they deployed piers steel planking, salvaged from bridge building supplies, but this material proved inadequate, warping and buckling severely under the intense tropical heat. Their efforts to compact the soil using heavy rollers also met with failure, as the rollers themselves frequently became mired in the intractable mud. By mid-August, Henderson Field was, at best, operational for perhaps 3 days out of 7. On the days it was unusable, the Marines on the ground found themselves entirely exposed and vulnerable. The absence of air cover rendered them susceptible to indiscriminate shelling from Japanese naval vessels, and allowed enemy troops to be reinforced under the cloak of darkness, without fear of aerial interdiction. The stark reality was undeniable and brutally simple. Without a reliably functional, all-weather runway, Guadalcanal would inevitably fall. Should Guadalcanal be lost, the entire Pacific offensive would be critically delayed, potentially for a year or even longer, with devastating strategic implications. Back in Washington, D.C., the critical issue of the incapacitated runway at Guadalcanal became an urgent priority, landing squarely on the desk of the Army Corps of Engineers. They were receiving increasingly desperate radio dispatches from the Pacific, all conveying the same urgent plea. "We need a solution, and we need it yesterday." Fortunately, the Corps of Engineers was not entirely unprepared for this challenge. They had been grappling with the persistent problem of constructing runways on soft ground since before the attack on Pearl Harbor, conducting extensive tests at various airfields ranging from the marshy environments of Louisiana to the frozen expanses of the Alaskan tundra. However, every solution they had thus far attempted had ultimately proven deficient in one way or another. Now, they were witnessing the real-time, catastrophic consequences of these past failures unfolding 7,000 miles away in the Pacific theater, adding immense pressure to find a viable answer. The first significant endeavor to address the soft-ground runway problem occurred in early 1941, when engineers meticulously tested a material known as square mesh track. This innovative design consisted of a robust grid of welded steel bars, visually resembling an industrial-strength chain-link fence constructed from rebar. The underlying theoretical principle was sound: to create a rigid framework capable of distributing the immense weight of aircraft across a broader surface area, thereby reducing localized pressure. They meticulously laid this material at Langley Field in Virginia, and proceeded to roll a B-17 bomber, weighing approximately 30 tons, across it. To their dismay, the square mesh track folded and crumpled under the bomber's immense weight, much like tinfoil. It became evident that the steel was insufficiently thick to withstand the concentrated pressure exerted by the aircraft's landing gear. However, increasing the thickness of the steel to provide the necessary strength would have rendered the material prohibitively heavy, requiring an entire cargo ship merely to transport enough mesh for a single runway, making it impractical for wartime logistics. Subsequently, the Hessian mat experiments were conducted in the spring of 1941, following reports from British engineers, who had achieved some degree of success utilizing burlap fabric coated in asphalt as a temporary roadway material in North Africa. American engineers hypothesized that if this material proved effective for vehicular traffic, it might also serve for aircraft operations. They painstakingly saturated thousands of yards of heavy jute fabric in hot asphalt, then meticulously laid it across soft ground at Wright Field in Ohio, where they initiated landing tests with P-40 fighter aircraft. The inaugural landing proceeded without incident. However, the second landing resulted in the creation of noticeable ruts. By the 10th landing, the fabric had completely disintegrated, tearing apart, and chunks of the asphalt-soaked burlap began to jam the intricate mechanisms of the landing gear. Consequently, the entire concept was relegated to the rejection pile by June, deemed unsuitable for its intended purpose. The approach involving coral and gravel initially appeared more promising, primarily because it mimicked the natural characteristics of hardpan surfaces. In July 1941, engineers meticulously constructed test runways using a composite of crushed coral aggregate blended with volcanic rock, materials that were readily available in abundance on many Pacific islands. This mixture was then compacted with steamrollers until it achieved a remarkable, concrete-like hardness. For a period of 3 weeks, the test runway performed flawlessly, enduring continuous aircraft operations without any signs of degradation. However, its resilience was shattered by the arrival of a tropical deluge, not a mere sprinkle, but a proper monsoon that dumped an astonishing 6 inches of rain in just 2 hours. The entire carefully graded surface rapidly transformed into a treacherous slurry. Engineers watched in dismay as deep gullies, large enough to conceal a man, developed across the runway. Worse still, once coral becomes saturated and begins to break down, it becomes almost impossible to recompact effectively, essentially necessitating a complete reconstruction of the runway. Pierced steel planking, PSP, emerged as the most viable solution among the alternatives, coming closer to success than any other material tested. Initially developed by the British for the rapid construction of temporary roads, PSP consisted of flat steel plates, each approximately 10 feet in length and 15 inches in width, perforated with numerous holes designed to reduce weight and enhance traction. The United States military commenced testing PSP for runway applications in August 1941 at Bolling Field. Engineers were particularly impressed by the speed of its installation. A runway could be effectively shingled in a matter of days rather than weeks. However, PSP possessed a critical flaw when exposed to tropical heat. Steel naturally expands when heated, and under the intense equatorial sun, these plates would inevitably buckle and warp, creating hazardous ridges that could potentially shear off aircraft landing gear. Pilots reported that landing on a warped PSP runway felt disturbingly similar to touching down on a washboard while traveling at a speed of 80 miles per hour, highlighting the severe operational risks. By the autumn of 1941, the engineering teams tasked with this critical problem were rapidly exhausting their innovative ideas and running perilously short on time. The events of December 1941, specifically the attack on Pearl Harbor, dramatically altered the strategic landscape. It was not merely a military catastrophe. It served as an urgent wake-up call, underscoring that the Pacific theater would demand novel solutions that had yet to be conceived or invented. In response to this pressing need, the Corps of Engineers issued an urgent contract request to American steel manufacturers, outlining stringent requirements. We require a runway surface that can be installed in a matter of days, capable of supporting aircraft weighing up to 50,000 pounds, performing equally well in both mud and coral environments, and durable enough to withstand tropical conditions without warping. Furthermore, it must be light enough to be transported across an ocean on cargo vessels already heavily laden with tanks and ammunition. The Carnegie Illinois Steel Corporation, situated in Pittsburgh, ultimately secured this crucial contract. Their lead engineer, James Marston, meticulously reviewed the extensive history of previous failures and arrived at a profound realization. Everyone had been approaching the problem from an incorrect perspective. Prior efforts had focused on attempting to create a surface that mimicked the properties of concrete or compacted earth. Marston's insight was elegantly simple yet revolutionary. Don't fight the mud. Float on top of it. He immediately began sketching a design that bore little resemblance to a conventional road surface, envisioning instead something akin to a flexible metallic carpet. By February 1942, Marston's dedicated team had successfully developed a working prototype. This innovative steel plank measured precisely 10 feet in length and 15 inches in width, but nearly every other aspect of its design represented a significant departure from existing technologies. Firstly, its thickness was a critical element, 3/16 of an inch of high-strength steel. This specific gauge was robust enough to resist buckling under the substantial loads imposed by aircraft, yet sufficiently thin that each individual plank weighed only 66 pounds. This weight made it manageable for 2 men to manually maneuver and position without the need for heavy machinery. The engineers strategically punched rows of holes across the entire surface, creating a distinctive pattern that resembled an industrial cheese grater. These perforations were not merely aesthetic. Each hole served 3 vital purposes. It reduced the overall weight of the plank by approximately 30%, allowed water to drain through rather than accumulating on the surface, and created numerous edges that provided aircraft tires with enhanced grip and traction. However, the true stroke of genius resided in the design of the plank's edges. Both of the long sides of each plank featured meticulously engineered interlocking mechanisms that Marston's team had spent months perfecting. One edge incorporated a raised lip, terminating in a hooked end that curved distinctly upward. The opposing edge was designed with a corresponding channel, precisely shaped to receive this hook. When 2 planks were laid side by side, the hooked lip of one plank would smoothly slide into the channel of the adjacent plank and securely lock into place, not with bolts or welds, but solely through mechanical pressure. This connection was robust enough to allow a 50,000-pound aircraft to traverse the seam without the planks separating, yet it retained enough flexibility that the entire mat could bend and conform to uneven ground without fracturing. The short ends of each plank employed a different, yet equally effective, interlocking system. A simple overlapping joint where the end of one plank would slide underneath the next. This arrangement created a continuous, unbroken surface spanning the entire length of a runway, devoid of any gaps wide enough to snag an aircraft wheel. Furthermore, this overlapping design meant that as weight was applied downwards, the planks actually locked tighter together, rather than spreading apart, enhancing the overall stability and integrity of the runway, rather than allowing them to spread apart. In March of 1942, the United States Army conducted exhaustive trials at Camp Claiborne in Louisiana, a location intentionally selected for its notoriously soft, almost impassable soil, which closely resembled the challenging mud of the Pacific Theater. Engineers meticulously deployed 1,200 square feet of Marston's innovative interlocking planks directly onto the unprepared, swampy ground. A fully loaded B-17 bomber was then maneuvered across this makeshift runway. Observers noted the mat's remarkable flexibility. It was visibly seen to ripple and undulate under the immense weight, yet it steadfastly maintained its structural integrity. Over a period of 3 days, a rigorous schedule of 50 takeoffs and landings was executed. The mat sustained only minor surface abrasions, exhibiting absolutely zero structural failures. Upon lifting a section for closer inspection, it was discovered that the underlying ground had compressed approximately 2 inches, but crucially, the ingenious interlocking system had distributed this compression uniformly, preventing any stress fractures or separation at the seams. Convinced by these irrefutable results, the military promptly placed an order for an astounding 60 million square feet of the material. Grasping the fundamental reasons behind the efficacy of these mats necessitates an examination of the physical principles at play when a colossal 30-ton bomber alights upon yielding terrain. The core issue does not lie with the aircraft's overall mass. Rather, it is the intense concentration of that weight. Consider, for instance, a B-25 Mitchell bomber, which, when fully laden, tips the scales at around 35,000 pounds. This entire formidable mass is channeled downwards through just 2 main landing gear struts and a single tail wheel. With each main gear equipped with 2 tires, the colossal 35,000 pounds becomes acutely focused onto a mere 4 square feet of contact area. This translates to an astonishing pressure of nearly 9,000 pounds per square foot impacting the ground with every single landing maneuver. In stark contrast, soft soil can typically withstand a meager 300 pounds per square foot before it begins to give way under duress. One does not require advanced mathematical computations to discern the gravity of this disparity. The Marston mat ingeniously resolves this predicament through its unparalleled ability to distribute the load across multiple planes, quite literally, a multitude of individual planks functioning cohesively as a unified, integrated system. Ask US to stay with US and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. When a landing gear wheel makes contact with an individual plank, that single plank is not left to bear the burden in isolation. The intricately designed interlocking hooks and channels ensure that the applied force is instantaneously transmitted to the 4 adjacent planks, 2 positioned on either side, and 1 directly in front and 1 behind. These planks, in turn, further disseminate the load to their respective neighbors, creating a cascading effect of force diffusion. Consequently, by the time the initial 9,000 pounds per square foot of pressure reaches the actual ground beneath the mat, it has been effectively spread across an approximate 100 square feet of the mat's surface. The underlying soil now experiences a dramatically reduced pressure of only about 90 pounds per square foot, a figure comfortably within the load-bearing capacity of even the most problematic and unstable ground. The inherent flexibility of this ingenious system is as critically important as its formidable strength. Conventional concrete runways, by their very nature, are rigid structures. This rigidity performs admirably on solid, stable foundations, yet it proves catastrophically inadequate on soft, unstable ground. Should one section of a concrete slab settle even minimally lower than the surrounding area, the unyielding slab inevitably cracks. Once compromised by a fracture, water infiltration rapidly ensues, leading to the swift and widespread deterioration of the entire structure. Marston mat, however, does not suffer from cracking precisely because it makes no attempt to be rigid. Each individual plank possesses the capability for minute, independent movement. We are speaking of mere fractions of an inch, while steadfastly maintaining its crucial interlocking connection. The entire runway surface, therefore, essentially floats upon the ground like a colossal steel raft, seamlessly conforming to any underlying settling or shifting without fracturing or breaking apart. The distinctive holes punched through each plank serve a purpose far beyond simply reducing the material's weight. They are instrumental in creating what engineers refer to as a semi-permeable surface. During periods of rainfall, a persistent and often torrential occurrence in the Pacific theater, water does not accumulate on the runway's surface, which would otherwise create treacherous hydroplaning hazards. Instead, it drains efficiently and directly through these perforations. But here lies the truly ingenious aspect. The holes measure only about 2 inches in diameter. This precise sizing ensures that aircraft tires, which are considerably wider, still encounter an abundance of solid steel surface for optimal grip and traction. The tire, in essence, perceives a continuous, solid platform, while water encounters an effective, integrated drainage system. Testing conducted at Wright Field in April 1942 conclusively demonstrated that water cleared from a Marston mat runway 6 times faster than it did from conventional solid surfaces. The interlocking edges also provided an unexpected, yet profoundly critical, solution to the problem of bomb damage repair. When an enemy bomber, such as a Japanese aircraft, inflicted a crater upon a Marston mat runway, the damage could not be simply patched in the manner of concrete. Instead, entire sections necessitated replacement. However, owing to the plank's design, which allowed them to interlock without the need for welding or bolting. Repair crews could effortlessly disengage the damaged planks, slide them out, and drop new ones into place. At Henderson Field, engineers meticulously timed this process. A bomb crater that had obliterated a 20-foot section of runway could be fully repaired and rendered operational again in under 40 minutes. This remarkable speed did not even include the time required to backfill the crater itself, focusing solely on the replacement of the matte surface. Contrast this efficiency with concrete, where a comparable repair might consume days and demand specialized equipment for pouring and curing new material. The inherent simplicity of the system meant that training requirements were minimal. There was no need for highly specialized engineers to install Marston matte, only personnel capable of following a clear pattern and working with speed and diligence. The scene is set at Henderson Field, August 17, 1942. The inaugural shipment of Marston matte arrived on Guadalcanal aboard cargo ships that had valiantly navigated a perilous gauntlet of Japanese submarines to reach their destination. Personnel from the Naval Construction Battalion, widely known as the CBs, labored tirelessly to unload 36 tons of steel planking onto the beach, all while Zero fighters relentlessly strafed the shoreline. Their monumental task was governed by a deadline measured not in days, but in precarious hours, anticipating the next inevitable Japanese bombing raid. Astonishingly, the CBs had never encountered this material before. Most of them were, just months prior, civilian construction workers, carpenters, steelworkers, and equipment operators recruited from projects building highways and bridges across the American landscape. Now, they found themselves thrust into an active combat zone, striving to decipher the intricacies of assembling a functional runway from scratch, all while actively enduring enemy gunfire. The first stark realization that dawned upon them was that 66 pounds per plank, while seemingly manageable in theory, became an arduous burden when those planks had to be transported hundreds of yards in oppressive 100-degree heat and stifling 90% humidity. Out of sheer necessity, they rapidly developed an efficient rhythm. Teams of 2 men would retrieve planks from the stockpiles and painstakingly haul them to the edge of the nascent runway. A 3rd man assumed the crucial role of guide, meticulously positioning each plank to ensure the precise alignment of its interlocking edges. The initial row proceeded with relative ease, simply involving the placement of planks side by side on the cleared ground. However, every subsequent row demanded the intricate engagement of the hook and channel connection. The ingenious technique they devised involved tilting the new plank at a slight angle, carefully sliding its hook beneath the channel of an already positioned plank, and then dropping it flat. When the plank properly seated, a distinctive metallic click resonated, a sound that quickly became the most profoundly satisfying auditory signal these men knew. That unmistakable click signified a secure lock. The arduous work unfolded in frantic, intense bursts, precisely timed between the relentless air raids. Japanese bombers were assaulting Henderson Field almost daily, often twice within a single 24-hour period. The resourceful CBs quickly learned to vigilant watch for spotters. The appearance of a solitary reconnaissance plane signaled that bombers were likely no more than an hour away. When the urgent call to action sounded, every man immediately dropped his tools and sprinted for the relative safety of the foxholes. The bombers would then sweep overhead, unleash their devastating payloads, and depart. The CBs would patiently wait a mandatory 10 minutes, allowing any unexploded ordnance to cook off. Then, with unwavering determination, they would return to the runway, resuming their work exactly where they had ceased. If a bomb struck a section they had already completed, they would promptly unlock the damaged planks and replace them. If, however, a bomb impacted an area they had not yet reached, they would simply fill the resulting crater with coral and continue laying the mat directly over it. By August 20th, a mere 3 days after the arrival of the initial mat shipment, a crucial section of runway, measuring 200 feet in length and 75 feet in width, achieved operational status. While this was not yet a full-length runway, Henderson Field would ultimately require 5,000 feet to safely accommodate bombers. It was entirely sufficient for fighter aircraft. That very afternoon, a pivotal moment occurred. 19 Wildcat fighters and 12 Dauntless dive bombers flew in from the carrier Enterprise. These aircraft, officially designated VMF-223 and VMSB-232, would go on to form the legendary Cactus Air Force, a moniker derived from Guadalcanal's distinctive radio call sign. They were landing on a surface that had literally not existed a mere 72 hours prior. The pilots reported that touching down on Marston mat presented a distinctly different sensation compared to concrete or compacted earth. There was a subtle give to it, a perceptible flex that could be felt through the landing gear. Some vividly described it as akin to landing on a firm trampoline. This inherent flexibility, in fact, made it more forgiving. Aircraft approaching with excessive force did not experience the violent bounces often associated with rigid surfaces, as the mat absorbed a significant portion of the impact energy. By September 5, 1942, Henderson Field boasted a complete Marston mat runway, stretching an impressive 5,200 feet long and 150 feet wide. The total installation time, remarkably, including all delays incurred from persistent air raids and artillery fire, amounted to just 19 days. Traditional concrete construction methods would have demanded a minimum of 3 months under ideal conditions, a descriptor that in no way applied to the harsh realities of Guadalcanal. While Guadalcanal unequivocally proved the fundamental concept, it was the subsequent developments that truly underscored the profound strategic value of these portable runway systems. By early 1943, the United States military was meticulously planning an ambitious island-hopping campaign across the vast expanse of the Pacific, an immense undertaking projected to span an eventual 7,000 miles from the Solomon Islands all the way to the Japanese home islands. Every single one of these islands would necessitate a fully operational airfield, and they would need it established with unprecedented speed. The entrenched Japanese defensive strategy hinged upon transforming each island into a formidable fortress, designed to withstand capture for many months. Marston mat, however, dramatically compressed and ultimately collapsed that protracted timeline. In February 1943, the focus shifted to the Russell Islands. The Marines landed, fully anticipating fierce and entrenched resistance, only to discover that the Japanese forces had already evacuated. Within a mere 60 hours of the initial troops hitting the beach, the indefatigable Seabees had constructed a fully operational fighter strip, meticulously laid with Marston mat. The sheer speed of this accomplishment was so astonishing that when Admiral William Halsey flew in to conduct an inspection, he directly inquired of the battalion commander whether they had commenced construction before the island was actually secured. They had not. Rather, their efficiency and operational tempo had simply reached an extraordinary, almost unbelievable, level. The newly established Russell Islands airfield immediately provided crucial air cover for the subsequent strategic leap up the Solomon chain, effectively reducing what would have been weeks of vulnerability down to a matter of mere days. The strategic vulnerability of newly acquired territories, previously measured in months, was dramatically compressed to a mere matter of days, fundamentally altering the pace of military operations. A pivotal moment occurred at Munda Point on New Georgia Island in August 1943. This particular engagement presented an unprecedented challenge, as the Japanese forces remained entrenched in formidable bunkers, strategically positioned to command the prospective airfield location. Undeterred, the Seabees undertook the perilous task of deploying Marston Mat under relentless, direct enemy fire. They conceived and implemented audacious, seemingly self-destructive tactics. One half of the battalion meticulously positioned the steel planks, while the other half valiantly suppressed enemy positions with a barrage of rifle and machine gun fire. This daring approach, though resulting in considerable casualties, specifically 14 servicemen tragically lost their lives and another 47 sustained injuries, proved remarkably effective. Astonishingly, the crucial runway achieved operational status within a mere 11 days. Even as Marine Corsair fighter aircraft commenced their combat sorties from Munda, Japanese snipers continued to be systematically eliminated from the immediate perimeter, highlighting the extraordinary speed of construction amidst ongoing conflict. The innovative spirit continued to evolve in November 1943 on Bougainville, where military strategists initiated groundbreaking experiments with prefabrication techniques for airfield construction. Rather than the laborious process of laying individual planks, engineers stationed in Australia began to preassemble substantial sections of Marston Mat into expansive panels, each measuring an impressive 50 feet by 15 feet. These colossal prefabricated units were then meticulously loaded onto LSTs, or landing ship tanks, and transported across vast distances without disassembly. Upon the LSTs making landfall at Bougainville, powerful cranes efficiently lifted these ready-made sections directly onto specially prepared ground surfaces. This revolutionary method drastically reduced construction time. A runway that would traditionally have demanded 2 weeks for plank-by-plank installation was completed in an astonishing 4 days. By the close of December, Bougainville boasted 3 fully functional Marston Mat runways, ingeniously arranged in a triangular configuration that facilitated simultaneous takeoffs and landings, irrespective of prevailing wind conditions. Please stay with us and watch until the end of this video. We would be incredibly grateful for your like and subscription. Also, we encourage you to share in the comments where you are from and what your thoughts are on the fascinating topic discussed in this video. The sheer scale of Marston Mat production figures eloquently underscores the indispensable role this technology assumed within military logistics. In its inaugural year, 1942, Carnegie, Illinois, alongside 9 other prominent steel manufacturers, collectively yielded an impressive 8 million square feet of the specialized matting. The following year, 1943, witnessed a dramatic surge, with production escalating to a colossal 40 million square feet. By 1944, annual output soared to an astounding 60 million square feet, a quantity so immense that it could conceptually form a continuous runway stretching from New York to Philadelphia. The military's insatiable demand for Marston Mat became so pervasive that it inadvertently precipitated a critical steel shortage, impacting other vital wartime initiatives. Consequently, tank production experienced a temporary curtailment as industrial furnaces were strategically reprioritized for the manufacturing of runway matting. This intense focus continued into January 1945, particularly evident at Lingayen Gulf in the Philippines. During this particular operation, Marston Mat was deployed in a manner entirely unforeseen by its initial designers. Engineers ingeniously utilized the material by laying it across expansive sandy beaches, effectively fabricating immediate, robust piers and temporary roadways for the essential movement of supply trucks. They swiftly ascertained that the matting performed with equal efficacy in distributing the heavy loads of wheeled vehicles as it did for the immense weight of aircraft. This innovative application meant that crucial supply convoys, which would ordinarily become hopelessly mired in the soft beach sand, could now proceed directly and without impediment from their landing craft to inland supply depots, drastically improving logistical efficiency. In February 1945, the island of Iwo Jima became the site of perhaps the most iconic, yet often unrecognized, Marston mat installation of the entire conflict. The unique geological composition of Iwo Jima presented an extraordinary challenge. Its volcanic ash was so incredibly fine and unconsolidated that attempting to construct upon it was akin to building on powdered sugar. Traditional concrete construction proved unfeasible, as the pervasive ash would contaminate the mixture, preventing proper curing. Similarly, the creation of compacted earth foundations was rendered impossible due to the complete absence of actual earth, with only the ubiquitous ash present. Consequently, Marston mat emerged as the sole practicable solution. Resourceful engineers meticulously laid this vital matting across all 3 airfields on the island, a Herculean effort undertaken even as the brutal and protracted battle for Mount Suribachi continued to rage fiercely. With the cessation of hostilities in August 1945, military strategists largely anticipated that Marston mat would swiftly become an antiquated technology, rendered obsolete within a matter of months. The advent of peacetime was believed to usher in an era where ample time and resources would permit the construction of robust, permanent concrete runways. Consequently, vast quantities of the specialized steel matting were systematically stockpiled at various depots strategically located across the Pacific theater. Thousands upon thousands of tons of this material languished in cavernous warehouses, awaiting eventual disposal through scrapping or commercial sale, its utility seemingly exhausted. However, the seemingly settled fate of Marston mat was dramatically overturned on June 25, 1950. The sudden invasion of South Korea by North Korean forces plunged the U.S. military into a frantic race to establish air superiority within a combat zone severely lacking in developed infrastructure. In this urgent crisis, the previously discarded stockpiles of Marston mat were hastily retrieved from storage. The Korean peninsula's topography presented a stark contrast to the tropical Pacific islands. It was a mountainous region characterized by exceptionally harsh winters, and soil that would freeze to an unyielding solid state. Engineers initially harbored doubts about the mat's efficacy in sub-zero temperatures, given its original design for humid, tropical environments. They swiftly discovered that while the steel itself exhibited increased brittleness in extreme cold, its ingenious interlocking design maintained structural integrity. Crucially, the inherent flexibility that enabled the mat to perform so effectively on soft, yielding ground also proved advantageous on frozen terrain. As the soil froze and expanded, the mat gracefully flexed upwards. Conversely, when it thawed and contracted, the mat smoothly settled back into place, preventing any cracking or separation. The Kimpo Airfield, strategically located near Seoul, served as a critical proving ground for this repurposed technology. By September 1950, the airfield lay in utter disarray, its concrete runways systematically demolished by retreating North Korean forces. Undeterred, U.S. Air Force engineers embarked on an extraordinary feat, laying Marston mat directly over the shattered concrete debris, thereby miraculously creating a fully operational runway within an astonishing 72 hours. F-86 Sabre combat aircraft commenced their missions from Kimpo, even as dedicated concrete repair crews continued the arduous task of jackhammering rubble on adjacent, still damaged sections. Throughout the Korean War, A remarkable 38 airfields ultimately benefited from the deployment of Marston mat. During this period, the military officially adopted a new designation for the material, PSP, or pierced steel planking. While the original name, Marston mat, gradually receded from official lexicon, the fundamental technology remained entirely unchanged and equally effective. In 1965, during the Vietnam conflict, the ubiquitous matting once again made its appearance, now nearly a quarter-century after its initial conception. Remarkably, some of the very same steel planks utilized on Guadalcanal 2 decades prior were still found to be fully functional and were redeployed. Engineers strategically laid this durable material at key locations such as Da Nang and Bien Hoa, thereby establishing vital dispersal paths for helicopters and expanding the capacity of existing runways. The challenging Vietnamese climate, characterized by torrential monsoons, intense heat, and acidic soil conditions, bore striking similarities to the Pacific Islands for which the mat was originally engineered. Consequently, its performance proved to be precisely as robust and reliable as it had been in 1942. However, the narrative of Marston mat takes an intriguing and entirely unforeseen trajectory following the Vietnam War. Post-conflict, the versatile material transitioned into a variety of civilian applications. Notably, oil companies began to adopt its use in the harsh, remote environments of Alaska and Canada. Here, it served to construct temporary access roads and drilling pads across delicate permafrost landscapes, crucially achieving this without inflicting permanent damage upon the fragile tundra ecosystem. The identical principles of weight distribution that once prevented heavy bombers from becoming mired in the soft Pacific mud now effectively prevented massive trucks from inducing the melting of permafrost. Remarkably, even environmental advocacy groups extended their support for its deployment, primarily due to its inherent removability. Upon the conclusion of drilling operations, the matting could be simply retrieved, allowing the underlying tundra to recover naturally, a stark contrast to the lasting impact of conventional, permanent gravel roads. In January 2010, a catastrophic magnitude 7.0 earthquake unleashed widespread devastation upon Port-au-Prince, Haiti. While the international airport's primary runway miraculously remained intact, the surrounding essential infrastructure was utterly obliterated, leading to severe logistical bottlenecks for critical relief flights. In response, the U.S. military swiftly airlifted numerous pallets of Marston mat, a testament to its continued production, and expertly deployed it across the damaged taxiways and parking aprons. This rapid intervention enabled cargo planes laden with vital medical supplies and sustenance to unload efficiently, and then taxi to newly established parking areas that had not even existed a mere 48 hours prior. Thus, a technology originally conceived and perfected for prosecuting war against the Japanese Empire was now instrumental in delivering aid and saving the lives of earthquake victims. Contemporary military forces globally continue to maintain substantial stockpiles of this adaptable material. The U.S. Air Force currently designates it as AM2 matting, signifying aluminum membrane version 2, reflecting a strategic shift from steel to lighter aluminum alloys to significantly reduce overall weight. Despite this material alteration, the fundamental design remains instantly recognizable. It features the same distinctive interlocking edges, an identical perforated surface, and adheres to the core conceptual principles first envisioned by Marston in 1942. The British Royal Air Force regularly employs it, and NATO forces notably deployed it in Afghanistan to expand crucial parking areas at Bagram Airfield. Its utility extends beyond military applications, frequently appearing in disaster zones following typhoons, floods, and hurricanes, essentially anywhere there is an urgent requirement for instant infrastructure on compromised or undeveloped terrain. Furthermore, remnants of the original Marston mats persist to this day. Sections can be discovered repurposed as pedestrian walkways, robust bridge decking, and even unique decorative fencing. Astonishingly, some Pacific islands still feature operational sections originally laid during World War II, now visibly weathered and worn by time, yet remarkably still performing their intended function after more than 80 years. While popular historical accounts and compelling documentaries often attribute victory in wars to the dramatic exploits of tanks, aircraft, and naval vessels, the tangible reality is that conflicts are frequently decided by the unseen, underlying infrastructure. It is the often overlooked logistics, the meticulously managed supply chains, and the extraordinary capacity to transform an otherwise unremarkable patch of ground into a fully operational military asset with unprecedented speed, far exceeding enemy expectations, that truly determine outcomes. In this crucial context, Marston mat fundamentally redefined the strategic parameters and operational possibilities of the Pacific War. Yet, despite its profound impact, the vast majority of individuals remain entirely unaware of its existence. Prior to the advent of these ingenious steel planks, the strategic capture of an island necessitated a commitment to many months of intensive construction before that territory could realistically become militarily useful. The process invariably involves seizing the ground, followed by a protracted period of waiting, while engineers meticulously surveyed the terrain, painstakingly graded surfaces, poured concrete, and then endured the necessary curing time. Throughout this extended interval, the invading forces remained perilously vulnerable, and the newly acquired island was, in essence, merely an exorbitantly costly piece of real estate. The Japanese military, with acute strategic foresight, perfectly comprehended this critical equation. Their meticulously crafted defensive doctrine explicitly relied upon the assumption that each captured island would consume such an extensive period to render operational that American offensive momentum would inevitably falter. Their tactics involved digging in deeply, exacting a heavy toll in blood for every inch of contested ground, and even in the event of an American victory, the victors would be effectively immobilized for months, engaged in the laborious task of making the island functional. The very concept of island hopping was, by this understanding, inherently designed to be a slow and arduous process. Marston mat, however, decisively shattered that deeply ingrained strategic assumption. Suddenly, it became entirely feasible to land on an island and have fully operational aircraft launching missions from its newly established airfields within a single week, and remarkably, sometimes even within a mere few days. This revolutionary capability fundamentally transformed the potential for American offensive aggression. Islands that had previously been considered significant strategic liabilities, precisely because their development would consume too much valuable time, now instantly became viable and attractive targets. The remarkable success of the Central Pacific Campaign, encompassing critical engagements such as Tarawa, Kwajalein, and Saipan, was directly attributable to the fact that newly captured islands could almost instantaneously provide forward operational support for subsequent assaults, rather than imposing costly and momentum-killing pauses in the advance. The statistical data unequivocally highlights the profound impact. By the conclusion of 1944, the United States military had successfully engineered and constructed more than 300 airfields throughout the vast Pacific theater. A staggering proportion, approximately 220 of these crucial installations, incorporated Marston mat in either a partial or complete capacity. Absent this innovative technology, it is estimated that perhaps only a third of those airfields would have been constructed, and their completion would have demanded 3 times the actual duration. Such a scenario would have inevitably led to a significantly diminished number of forward operational bases, necessitating considerably longer flight distances for strategic bombers, and consequently, a substantial reduction in vital air coverage for naval operations. Ultimately, the entire chronological progression of the Pacific War could have been fundamentally altered, potentially extending its duration by many months, or even a full year. The progression of events, the temporal shifts, could stretch by many months, perhaps even a full year. Consider, for instance, the pivotal bombing campaign waged against Japan itself. The formidable B-29 Superfortress aircraft, whose relentless sorties ultimately compelled Japan's capitulation, originated predominantly from the Marianas Archipelago, specifically the islands of Saipan, Tinian, and Guam. These strategically vital territories were secured during the summer months of 1944. Remarkably, by November of that same year, a mere 5 months thereafter, these same islands were already serving as launch pads for extensive aerial assaults targeting Tokyo. This astonishing feat was solely attributable to the fact that military engineers possessed the capacity to rapidly deploy Marston mat runway systems, robust enough to accommodate the most substantial bomber aircraft within the American military's inventory, within an astonishingly brief period of weeks. Conventional concrete infrastructure development, in stark contrast, would have postponed the commencement of those crucial aerial operations until mid-1945 at the absolute earliest, fundamentally altering the strategic computations for the conflict's conclusion and potentially prolonging the global struggle. There is a more expansive insight to be gleaned here, concerning ingenious problem-solving amidst extreme duress. The industrial giant Carnegie, Illinois, notably, did not conceive of some esoteric new substance or a groundbreaking new method of production. Instead, their brilliance lay in scrutinizing pre-existing methodologies for steel construction and posing more incisive inquiries. How might one achieve robustness devoid of inflexible stiffness? How could minimal mass be attained without compromising structural integrity? And crucially, how could intricacy be rendered sufficiently straightforward such that fatigued personnel, operating amidst hostile engagement, could erect it accurately? The true sophistication resides in its straightforwardness. Interlocking panels designed for effortless connection, perforations engineered for efficient water egress, and a metallic composition engineered to yield without fracturing. Chroniclers of military campaigns frequently characterize the Pacific War as an aircraft carrier war, a submarine war, or a conflict defined by the intricacies of logistics. While undeniably accurate, beneath this layer of strategic discourse lies a more fundamental truth. It was a war defined by the resolution of intricate engineering challenges against seemingly insurmountable temporal constraints. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please leave a comment below, telling us where you are from, and what you think about the video topic. Indeed, the visionary Marston and his dedicated cohort at Carnegie, Illinois likely preserved a greater number of human lives and curtailed the duration of the conflict with greater efficacy than any solitary instrument of combat. Their profound impact stemmed not from acts of demolition, but rather from feats of creation. They brilliantly devised a method to transform treacherous mudflats into operational airstrips, to convert dense tropical foliage into vital aerial command centers, and to elevate previously insignificant island territories into crucial strategic embarkation points. In essence, they rendered the previously insurmountable logistical hurdles entirely attainable. And it is an immutable truth that in the crucible of war, the very essence of warfare hinges upon logistical mastery. These ingeniously designed, perforated steel panels, characterized by their unembellished interlocking mechanisms, did not merely facilitate the construction of airstrips, they forged the path to victory.